So what do we mean by enthalpy change, the energy change in a reaction? Well, we have a reaction and molecules ready to react. Before these molecules can react though, we need to break the bonds. We have to put energy in to break those bonds apart. We give it a positive enthalpy value, it's endothermic. At the product side, we're going to be making bonds, and this is exothermic. Making those bonds releases energy. The overall enthalpy change for the reaction depends on which is bigger, the breaking or the making. Hess's law says that the enthalpy change for a chemical reaction is independent of the route taken. The enthalpy change for a reaction can be calculated using Hess's law given appropriate data. Well, if we think about this in terms of everyday life, maybe you've got a favourite place where you like to go and read a book. You can get that way, either going via the school over to your favourite place, or you could go via the hospital and to your favourite place that way. It doesn't matter which of the routes you take, it's the same distance either way. And if you know how far it is in one direction, then you're going to know how far it is in the other direction. We can use this in chemical reactions, the enthalpy change for one route but not the other, and we can figure it out that way. One way to look at Hess's law is working with cycles. In this situation, we have a start point, we have an end goal, and we have different ways to get there. I could make sodium chloride by reacting hydrochloric acid with solid sodium hydroxide. Alternatively, I could start by dissolving up my sodium hydroxide in water, and then I could react it with the hydrochloric acid to get my aqueous sodium chloride and my water solution. Both routes should have the same total enthalpy change. If we know 2 out of the 3 enthalpy change values, we can figure out the third. So here's an example of a cycle question. Consider the reaction pathway shown below. According to Hess's law, the enthalpy change value in kilojoules per mole for reaction Z to Y is, and we've got a selection there. The thing you really have to do with these cycle questions is follow the arrows, look at these arrows and figure out where they're all pointing to. Where is the origin and where is the end point? Once you've got that, you can just set up a little equation and solve for the missing value. This is because Hess's law says it doesn't matter which route you take to get to your destination, the overall enthalpy change will be the same. So Wz plus Zy will equal Wx plus Xy. So we've substituted the values into the equation and we just need to solve it now. So the result shows us that the answer is A. More often though, the questions we get are working with equations and it can be tricky to draw cycles for them. There's always a target equation for which we don't know the enthalpy change, and then we'll be given 2, 3, 4 sometimes equations where we do know the enthalpy change value for those reactions, and we have to manipulate these equations to match up with our target and find the missing value. This is another occasion where highlighters are strongly recommended. Start by popping a box around your target equation, that helps keep it separate. And then what we're going to do is we're going to go through these equations and find something that matches up with the target equation. However, if there's something that appears in more than one equation, don't match that. You'll get yourself in an awful fankle. So the thing left for us to match in the first equation is the water. And things that I'm looking at when I'm matching them together, are they on the same side of the arrow in their equations? Are there the same number of moles? So the water here is on the opposite side of the arrow from this one. So to get this equation to match up with the target, I would have to reverse this equation. And if I'm reversing the equation, I reverse the enthalpy change for the reaction as well. There's not the same number of moles. There's twice as many moles in the target equation. So again, to get this to match, I'm going to have to times this whole equation by 2, and so I'll times the enthalpy value by 2 as well. For our second equation, we've got a choice of what we can match, so I would just pick the first thing in the equation. Again, is it the same side of the arrow? In this instance, yes it is. Are there the same number of moles? Yes it is. So we're just going to use this enthalpy value as it is without any alteration. Now we've got these two enthalpy values here, we just have to add them together and that will give us the enthalpy change for the target reaction. So the enthalpy change for our target reaction is minus 414 kilojoules per mole. Now the reason this works is that the bond breaking and bond making steps for these reactions add up to the same as the bond making and bond breaking steps for your target equation. I'm going to prove this to you by manipulating the equations in the same way as I did the enthalpy values. First of all, I'll reverse equation 1 and I'll times it by 2. Secondly, we'll just leave equation 2 as it is. Next thing, I'll bring these equations down here and I'm going to add them together. Next, I'll look for anything that appears on opposite sides of the equation and I'll cancel that out. So 1 mole of oxygen here, 1 mole of oxygen here. We break those bonds and then make those bonds exactly the same enthalpy change there. They're going to cancel each other out. Next up is the hydrogen. 1 mole of hydrogen here, 2 mole of hydrogen here. We can cancel this completely and cancel one of the hydrogens here. So if we compare what we're left with our target equation, you'll see they are identical. So by doing these manipulations, we have ended up with our target equation. Next example, as soon as you see these equations lined up, you know it's a Hess's law question and you get your highlighters out. So we're matching up and we're remembering to check, are things on the same side of the arrow? Are there the same number of moles? Equation 1, there's no carbon there, there's no hydrogen there. There is butene though, so I can match up the butene. Equation 2, no carbon, no hydrogen, no oxygen, but here we have butane 2O. That matches up as well. Great. Equation 3, hydrogen, oxygen, water. Water's the one we're going to match up. So for equation 1, we're on opposite sides of the reaction arrow, so we'll need to reverse this enthalpy change, this enthalpy value. Equation 2, same side of the arrow, same moles, we'll leave this one as it is. Equation 3, they're on opposite sides of the arrow, same number of moles, so we'll be reversing this enthalpy value. All we do now is sum these together to get the total. So that gives us a result of minus 43.9 kilojoules per mole as the enthalpy change for the target reaction. So here's another example. Why don't you try this one yourself? Just remember to check when you're matching up, are they on the same side of the arrow? Are they the same number of moles? And if you've got something that appears in two different equations, like here, you do not match them up. You'll get in a fankle if you try and do that. So pause the video now and play again when you're ready to check your answer. So in equation 1, we had this on opposite sides of the arrow, so it is reversed. Equation 2, same side of the arrow, but there's 3 moles in the target equation, so we're times them by 3. Equation 3, same side of the arrow, same number of moles, so we used it as it was. Adding up those enthalpy values gives us a total of minus 2168 kilojoules per mole. So this is a multi-choice question that's a little bit tricky at first glance, but it's really just a normal Hess's law question. We've got our equations, it's not clear which is the target at first glance, but if we look here at our options, A equals A equals A, A is going to be our target, and we're seeing what do we have to do with these other equations to get A. So now you know that we're matching for equation A there. Why don't you pause the video, have a go at this yourself, and press play when you're ready to check your answer. So I matched up. Equation 1, I need to reverse because we're opposite sides of the arrow. Equation 2, same side, same moles, use it as it is. Equation 3, same side, same moles, use it as it is. And that gives me, I have minus B plus C plus D, and I just have to match up with which answer fits that best. And I'm looking along, checking my signs here, and we'll find that A gives us that. They don't have it in the same order, but everything's got the correct signs. So hopefully now you know how to calculate the enthalpy change for a reaction using Hess's law. Big thing to remember is highlighters. The different colours will help you match up and keep your head straight when you're looking at what needs to be reversed and what needs to be multiplied and what you leave as it is.